I'm Roni from Mellanox. Today we're going to speak about 5G, challenges, about 5G and DPDK, and about 5G, DPDK, and RSS. Okay, so 5G is the 5th generation of cellular networks technology. This is the next generation, and it promises the following things: 100 times more connected device to the network, 1,000 times more bandwidth per unit area. I will explain each of the points in more details. 1 to 10 gigabits for a mobile device, through your user equipment, through your mobile device. Everything is VNF and SDN. Everything should be software defined. It's all planned to be run on the cloud. And ultra low latency. For some use cases, you want very low latency, as I will show you. Okay, for the first bullet, low latency. So 5G contains the concept of network slicing, when in some cases it will guarantee a very low latency of below 1 millisecond, and this means end-to-end. Some examples is for safety. This guy is crossing the road without looking in his mobile. The car is coming very fast. The driver also is not knowing what he is doing. There is a sensor that detecting the man walking on the road. The car is equipped with 5G SIM. It is connected to the local cell here, and this goes to the safety system that detects that there's going to be accident, and then it can send alarm to the car in this case, maybe a sound alarm like you have a Mobileye if you know, and maybe in the future it also will slow the car for you. Another example is VR and AR. AR is augmented reality. It is where you see the real surrounding of you, but on top of that, you're adding another picture. A nice example of that is for mapping. You are looking on your mobile phone, and you see the real picture, and an arrow that's showing you the way to where you want to go, and maybe an arrow on the restaurant you want to go. And this can be also on the car. You will see it like a pilot on the window, and you can see the arrows that pointing where you need to turn. 100 more number of connected devices. The reason behind that was IoT. If you heard about smart cities, smart agriculture, smart home, smart agriculture, for example, you have many sensors on the farmer field. They are all transmitting to some system, for example, how dry is the land, and if there is the system knows where to water the plants and where not, saving water. There can be drones flying over the fields and taking pictures of the plants, and using some machine learning algorithm, detect if you have a problem, for example, insects or diseases. Smart home, you can turn up the light from your phone. You can turn up the air condition before you arrive in home. You can open the door for where you have a package delivery. So you can open the door and turn on the camera and watch the guy put in the package where you want it to put, and so on. This means that there are a lot more connected devices at the same time. In 4G, the number of connected devices to one cell is around 200, no more, which is not a lot. There's also the density that I will talk on the next slide. 1,000 times more bandwidth per area. In 4G, there is a limitation of capacity. There is a number of cells, a maximum number of cells that you can put on a certain area. If you exceed this number, you're starting to get interference. So if each cell can do around, for 4G, it's around 50 megabits per second, and you look on an area, then the total throughput that you can generate is the number of cells. You multiply by 50, more or less. This is the maximum throughput. In 5G, the number of connected UEs is 100 more. So instead of 200 UEs, you can add 20,000 maybe. And the throughput is much higher. Instead of 50 megabits, the cell itself can generate even 20 gigabits. So you can, the potential of how much packets this area can generate for the mobile operator is huge. Okay, a large city in 4G. The numbers I'm saying is about years ago. This is my last update. Is around 20 gigabits. Okay, for a large city, London, I don't know, Houston. Now, if you take 20 mobile sets, you can generate this traffic. If you're asking yourself, why do you need so much data? The answer is that there are applications that need these rates. For example, virtual reality. In virtual reality, there's two problems. One is the resolution, because it's very close to your eyes. You see the pixels, so the current high definition is not enough. You need much higher resolution, which means a much higher bandwidth that you need. And the second is that you need to send all the surrounding, okay? Because when you're turning your head, you have to see what is in front of you here. So one solution for that is only sending the picture that in your direction, but then you need a very low latency. But usually what they are doing is transmitting the entire surrounding. Okay. So in 5G and DPDK, okay, for 5G, the packets per second is going to be huge. We want a very low latency. And a lot of the VNF that are going to run on the clouds are packet processors. Okay, they are not services like web services. They cannot benefit from TSO and LRO and all the hardware offload that are currently existing. There's also the cloud infrastructure. So you have to have a very fast packet delivery. Because if you run a VNF that need to process 100 gig is 20 million packets per second. So the infra should be able to deliver this packet to the right VNF. The switching should be very fast. And of course, the VNF acceleration itself, we will see example in a minute. And because everything is software defined, you will run on the mobile operator cloud. They will want that you maximize your PPS, and you minimize the CPU utilization. Actually, already today, we see they have their definition. You're allowed to use 20 cores, and you give us, I don't know, 10 million packets per second. This is what you have to do in order to get into our network. So more about 5G architecture. What we are mainly interested, okay, first with the high level. The mobile phone is connected to the cell. This is the analog signal. We don't care about it so much. And then it's the mobile packet is translated into digital again, and then into a packet. And then there is an underlay, because in mobile environment, you are switching cell. Even when you are moving, your mobile phone can attach to a different cell. Even when you are standing, your mobile is connecting is negotiating with all the surrounding cells, and it will move you to the cell with the best signal. So you need an underlay that will keep your traffic to the mobile and from the mobile. And all this traffic is tunneled with the GTP tunnel. Okay, so it goes to the IUPF. UPF is the user plan function. We talk about it. And then the user plan function can be split into two. One is the backhaul, one is the front haul. And from the UPF, it will go to the data network. Above the dashed line is the control. You have authentication and mobility function, session management function, and so on. But most of the data, most of the packets per second are going through the data plane, the UPF. One interesting use case in 5G is what we call a MAC, multi-access edge computing. The idea behind that is that there's going to be a lot of load if 10 devices can generate 20 gig of traffic. You cannot let this traffic go to the core. Okay, your core will be loaded and congested. You cannot supply this throughput to the mobile. So the idea is that you have a cloud on the edge that will do the services. You should be able to divert some of the traffic. In this example, this is an example I saw a few times in a few startups and also big companies. This is for gaming. You have a weak hardware phone, and you want to play a game that has a graphic. So what you do is that all the compute of the graphic is done on the server on the edge, and your mobile phone is just rendering a video. So your mobile just needs to show video. It doesn't need a very strong hardware, and the compute is done on a very strong server, but it has to be close to the edge in order to have a low latency and in order not to load the core network. And for this, you need, for implementing this, you need some entity, some VNF that knows to register this gaming and knows to identify the traffic that should be diverted to this gaming. And this all should run in a very high packets per second. In order to do that, you need to inspect every packet that is passing and know to divert it to the right direction. Another place in 5G that is interesting is that in 5G there's a concept, there's a PDI and PDR. PDI is a way to identify some of the traffic. The traffic you can identify by the GTP tunnel, for example, and maybe GTP plus 5 tuple. And then after you have this match, you have to do some certain of actions. It looks just like RTE FLOW. Okay, RTE FLOW is the best for offloading that. After you have a match, you have some actions. For example, count because there is a billing. You do decap because you're going to the data network. You don't need the GTP. In some cases, you need to do NAT because you're going out to the network, so you have to change the source IP. And in some cases, you have quality of service. For example, if you have a VNF that is implementing that, it can benefit from the hairpin because it could, after the first few packets that the UPF is being configured by the SMF, which will define those the match criteria and the action criteria, you can offload the entire processing to the hardware. Okay, now I get into RSS. So first, 5G, like 4G, the traffic is tunneled over GTP. GTP is a very simple protocol. It is divided into GTP-U and GTP-C. Basically, they have the same initial header, but GTP-C is a control protocol. So after the initial header, it has many types of messages. But this is the control, and there are not a lot of messages. The GTP-U, what is interesting for data plane functions is the tunnel, because the tunnel identifies the UE, and maybe looking inside the IP, the inner IP and layer 4 header. Okay, so now we're getting to the problem of RSS. Now, if you want to write a VNF that will run, you will do some of the user plane function. If you are located on the edge here, that the traffic goes to the data network, and on the other side is go to the RAN, to the radio access network, you have asymmetric traffic. From one side, you have packets that is coming from the data network to the RAN is not tunneled. Okay, you have just a packet. Probably the destination IP is a NAT IP. You have to change it, but we'll get to that later. The other traffic that is going to the data network is tunneled. You have GTP. So if you are using just an RSS, a regular RSS, for the traffic that is going to the data network, you have a problem because the 5-tuple will be identical. In GTP, there's no entropy. You are not changing the source port or doing some hashing. It's always the same port number on both directions. So the packet is exactly the same. If you are doing RSS, all the traffic of one cell will get exactly to the same core. And if you have 20 gig on one cell, you have a problem because if you are doing something with the traffic, one core cannot handle 20 gig. For the other direction, you can do RSS on the 5-tuple, but then you have another problem. Many of the functionality we want is per user equipment per UE. So if you do a 5-tuple RSS, the traffic will spread among all the cores instead of going to a specific core. Okay, this is how it looks like. The traffic, there is one mobile phone that is doing, at the same time, is watching Netflix and sending WhatsApp and doing another something, other application. And the traffic that is going to the data network all go to the same CPU because the RSS is done on the GTP layer on the outer. And the traffic that is coming back is spread between all the cores. And now each core gets few of the user flows. So the load is unbalanced. And in many cases, actually in most cases, you want a UE context. You want to handle the same UE in the same context. And doing the traditional or the existing RSS cannot handle this use case. So we have two types of RSS requirements. If you are in termination points means that you are going to untunneled network. So the traffic that is going to the untunneled traffic network, you should do the RSS on the inner source IP. Okay? You have a UE. The UE is tunneled. The traffic is going with GTP to the internet. You want that UE traffic to go to a single core. The only field in the packet that can identify this UE is the source IP in this case. So you want that the RSS will be done on the source IP only of the UE, of the inner header. The downgoing traffic to the RAN will have untunneled. In this case, the destination IP should be the UE IP, and you want to do the RSS on that. If you have a SNAT, if the IP was changed before the packet got to the data network, to the internet, when it gets back, you need first to replace the IP with, to do the revert for the SNAT, and only then do the RSS, or else you will get the packet, it won't be symmetric. Other use case is that you are what is called N9 interface. In this case, both directions are GTP. In this case, you want to do the RSS one side on the inner source IP, and the other side on the destination, on the inner destination IP. So what VNF providers, people that do security and doing user plane function and doing 5G stuff, what they do now, they have dedicated cores all the traffic is doing, you're doing the traditional RSS, and the packets go to a dispatcher. This is a dedicated core. The core is looking in a very big table, looking for the UE. You have to pass the packet, extract the inner source IP, look for the UE, find out where is the code that is handling it, and put the packet in the queue. This is very not efficient, and you're wasting cores, and it is not a good way to utilize your CPUs. Also, it limits the max number of PPS that you can do. If cell can do 20 gig, in some cases, you won't be able to handle it. Another solutions that currently exist in the market are hardwired configuration. In this case, you configure the NIC. It's some kind of hard-coded. If the packet is going to this direction, you do on the source IP. If it's going to that direction, you do it on the destination IP. This can work in some cases, but it's not flexible because in some cases, VNF might get two types of traffic. One, you want to do RSS in one way. On the other kind of traffic, you want to do it in a different way. In this case, you cannot differentiate between them. And also, if you have NAT, it will fail because you have to replace the IP, to return to do ANAT, and only then RSS. And in this case, you don't do that, so it will fail, and the packet will reach to a different core. So what we suggest to do is use RTE FLOW. It already has RTE FLOW API for RSS. This is how it looks like. You have level. 0 is the default. 1 means the outer. 2 means the inner. Maybe in the future, we might have more levels because you have underlay, maybe all of this one on VXLAN or something. The type means that you specify on which fields of the header you want the RSS to be done. Okay. In this case, we want to have a flavor of only source IP and only destination IP. And the key, if you're using a regular RSS, you can put here a symmetric key, and you will get the same RSS for both directions. So this already exists. Okay, this is example for test PMD. After we implemented it and we ran traffic of GTP. So traffic that coming, flow create 0 mean traffic that come from port 0, ingress coming inside. It's Ethernet, it's IPv4, it is GTP, do RSS, and on level 2. Okay, level 2 means the inner, and the types is source IP. We want to do the RSS on the source IP, meaning on the UE, on the UE IP. The traffic that is going to the other direction, we want flow create 0, mean from the other port in this case. It's Ethernet, it's IPv4, there is no GTP in this case. And the RSS that we want to do, it will be the default RSS, so 0 is the outer in this case. And the type is destination IP. Okay, so as we can see, the picture, there are 3 mobile phones, and each one is directed to a single core. So we can implement the UE context functionality easily without wasting cores on dispatchers or losing flexibility. Still, we have the SNAT problem. Many mobile operators, they have a limited amount of IPs. So when the traffic goes to the internet, they share the same IP between multiple UEs. So they have to do, they're doing SNAT. It's not that only that they are doing SNAT. The same IP is used for many UEs. So what you have to do in order to overcome this, you have to configure a flow table. Okay, this is a hardware solution. Use RTE FLOW to configure a flow table. If this is the destination IP and this is the 5-tuple, change the IP to the UE IP and the UE port, the port in this case, you probably do S0. You're changing also the source port. So you put it back, and only then you're activating the RSS, and then you can get the desired result that we saw in previous slide. So all the traffic of a single UE will get always to the same core. Another problem, this is a harder problem. In some cases, the service provider might allocate 2 IPs, one IPv4 and one IPv6. So RSS won't work here. Okay? In this case, you must do some kind of flow table in the hardware, changing the IP and direct the UE according to a predefined, you define it in the software. When you allocate the UE, you configure the hardware, you load balance, so a specific traffic of a UE, if it's IPv6, and if it's IPv4, if it's before the NAT or after the NAT, it will get to the same core. Or you can go back to dispatchers, and we saw that wasting cores and utilization. That's it. Thank you.
Any questions?
Hi, you mean RSS can work in GTP mode? Do you mean RSS can calculate hash index by GTP header such as TID?
Currently, no. There's no flexibility in this case, but there's no reason why not to do that in the future.
Oh, okay.
So the RTE FLOW API is not enabling that at the moment.
Okay, so RSS only can calculate hash index by 5 tuple, right?
Currently, it's calculated only on the header, IP header, and on the L3 and 4 header. You can specify with flags what you want: source IP, destination IP, source port, destination port, and protocol type.
Okay.
You can have any mix of them.
Okay, thank you.
Okay, great. Thanks a lot, Roni.
Okay.